I want to show you how to project one vector onto another and avoid the square root call. Let me draw our equations we've used several times. Vector A dot with vector B is equal to the magnitude of vector A times the magnitude of vector B times the cosine of the angle between them. And we normalized one of the vectors. Well, let's say we're going to normalize B, thus projecting A onto B. When we normalize, that turns one of these into the value 1, which is the same as multiplying by 1, which means we're left with A cosine theta. But what I want to do instead is avoid this normalized call. And if I get rid of this normalized call, normalize requires the square root. I'll click on this and F12. Hopefully you remember from the previous videos we use this magnitude, and the magnitude function requires a square root, and that can be expensive. And this, you could look at this and say, Jamie, you are prematurely optimizing. And I'm saying, yes, I am prematurely optimizing. I probably should not do this. But there's also education and value in what I'm doing, so I'm going to do it and show you how to do it. Again, when we take the dot product of two vectors, we get magnitude of those two vectors times the cosine of the angle between them, and I want to change one of these into 1. Well, if I don't use normalize, if I don't say normalize, that's going to leave the magnitude of B in here. I wonder if there's any magical math we could do to eliminate B besides the square root. Well, there must be, because I'm doing a video on it. Let me show you how to do that. When we take the dot product of two vectors and we get this result, let me just write this result by itself. Once we have magnitude of A, magnitude of B times the cosine of the angle between them. What if we turn around and say, hey, I'm going to divide this by the magnitude of B squared? Didn't we just do a function in the last video? We did magnitude squared. So I can say magnitude of B squared. Now I'm actually going to take this out and write this the long way. That's the same as magnitude of B times the magnitude of B. Well, look at this. I can cancel. That's quite nice. All right, let's erase what we just canceled. That magnitude of B divided by magnitude of B is 1, so they cancel each other out here. But then I'm left with this magnitude of B on the bottom. I need to eliminate that somehow. Well, do you remember after we did this normalized thing and we got our wall normal? That's normalized, meaning length 1, and normal, meaning perpendicular to the wall we're doing our test against. Once we take the ship velocity, we dotted that with the normal, which gave us essentially the magnitude of the ship velocity times the cosine theta, theta being the angle between the ship velocity and the normal. I could say it's the magnitude of the ship velocity times the magnitude of the normal times the cosine of theta. But if you remember, this little caret thing right there means n's length is 1, so that's the same as multiplying by 1 here. And all we're left with is the magnitude of the ship velocity times the cosine of the angle between the two vectors, which is what we want. This is what we got over here. Okay, that's why we did the normalized thing. But then once we have that length could be this direction, or that direction, or that direction, or that direction. Hopefully these are all kind of the same length. But if you get the idea, we have a length, but we do not have a direction. In order to get the proper direction, we then took that scalar, that number, and scaled, hence the term scalar, scaled the normal by that scalar, and that gave us the direction. I've said in previous videos that a vector is a magnitude and a direction. Well, in this case, here's the magnitude, and here's the direction, separated like so. Well, what if I went over to here? Let me just move that cosine theta over so I get some more screen real estate here. I have cosine theta, and then let's write B in its two parts, meaning magnitude and direction. So I'm going to write magnitude of B, okay, magnitude of B times its direction. Right, that may seem a little bit weird. I can say the vector B is equal to its magnitude, okay, its length. Length doesn't have any direction. So the vector B is equal to its length times its direction. That's totally legit. These two are equal. Remember, the direction is unit length 1, and then the bar on the left and the bar on the right denotes magnitude or length of the vector. Well, if I take this result here and times it by, essentially I'm timesing it by vector b here, and that's what we were doing down here. This is our b in this case. This is our normal. This is the vector we're projecting onto. In this case, we're trying to project onto b. Well, if I do that multiplication, that cancels this out and cancels this out. Let me erase those for you now. And what are we left with here? What are we left with? In fact, I can erase. That cancels. That leaves 1. I can erase all that. That leaves magnitude of a times the cosine of theta times the unit length vector of the vector that we are projecting onto. Okay, this is exactly what we wanted. This is exactly what we have down here. Okay, hopefully I didn't muddy the waters there too much, but that's exactly what we want. So after we do a dot product, we can then divide by the magnitude squared of the vector that we're trying to project onto. That's magnitude squared, and then multiply that result, that scalar number, times the vector we're trying to project onto. And thus we've eliminated the square root function. Right? And it also gives us a nice projectOnto function. We can make a function called projectOnto. And anyway, so in the next video, I'm actually going to implement all this crazy math. I hope it's not too crazy. It's actually pretty straightforward. I think when you see me write the code, you'll be like, oh, wow, that was really simple, and that does make sense. So we'll do that in the next video.